So I have created a rice chart for 4 of the examples from practice 1. But I want you to notice that I changed the E. So the ones that are complete solutions, what did I change the E to? I changed it to end because it is not equilibrium. So I wanted to keep the same format, but we need to understand that this is the end of the dissolving. And so like when we talk about reactions like combustion, combustions keep going until you run out of something and the reaction ends. It's not equilibrium. So we did these kind of charts where we kept track of amounts last semester, and we did limiting reactant kind of idea where one chemical that's a reactant, when you run out of it, that's the end of the reaction. So same kind of idea, but we're not doing mass. We're only doing molarity, which makes things easier. And so here is the way that we are going to use these tables. And so we got 2 types of tables, one where everything comes to an end and other where equilibrium is established. But both of these, we're going to create a table to show establishing equilibrium. So the amount of substance that dissolves is going to be our change for that substance. So if we have a homogeneous solution, which is the one-way arrow, the molarity of the solution is going to also be the change. So it's going to go in 2 places. So the way that you do this, if you know how much of a chemical you have, that will be your initial amount. Because that literally is that much of this. So they go together. So same idea, nothing's new. It's going to be 0.75 molar. So initially, when we started our solution earlier, I had a certain amount of sodium carbonate, and I had water, and in the water, was there any sodium or carbonate? No, there wasn't. Because initially, if it's water, if we're talking about water, water is not going to have sodium and carbonate floating around in it. 0. So this is our initial for dissolving something in water. This is how much of this substance that I'm going to end up dissolving. I didn't have any sodium or carbonate before. Okay, so if it is a homogeneous solution, the molarity of the solution is the change. So what is the change for sodium carbonate? 0.75. Because how much sodium carbonate dissolved? All of it. So whatever this number is, we're going to add or subtract. Subtract, because if you add, where's it coming from? So underneath here is going to be 0.75 molar. And so at the end, how much solid sodium carbonate was there? 0. And that means that we had no solid left. Okay. What happened to it all? It all turned aqueous, and as soon as it turned aqueous, it wasn't together anymore, it was separate. And so just a reminder, for change, everything is a mole-to-mole ratio. Okay. The change, that's change for the compound. The ions will be that molar ratio of whatever that factor is. So our factor is 0.75. Sodium is going to be what factor of 0.75? 2, because for change, it's always your coefficient. So it's going to be plus, because it's being created, 2 times 0.75. And what about carbonate? Plus 1 times 0.75. So at the end, when all of it dissolved, how much sodium was floating around? 1.50 molar sodium and 0.75 molar carbonate. So in that solution, there's double the amount of sodium ions because it's 2-to-1 ratio. So here, the first one, the amount of substance dissolved is the factor for change, but it's also your initial amount because it's the amount of that substance. It's homogeneous. That'll be the amount of compound, and your ions amount that gets created is going to be whatever mole ratio is. So it's 2 times that and 1 times that. So see if you can do the same kind of chart for lithium hydroxide. And you want to make little notes to yourself about where the numbers are coming from and why. So that there's going to be a lot of 0.75 because I just chose the same number. So like where it came from. That's what your table should look like for the lithium hydroxide. Again, make little notes to yourself where the stuff comes from. Because I don't want you to, I was trying to be consistent, but then you might think, well, you always put 0.75. No, you always put the amount of the chemical that dissolves, because we're talking about every single one of these problems is going to be this amount of chemical interacting with water. And so that molarity that you're given will be your initial amount. Okay. So what do we do if it's supersaturated? Do we have an initial amount? Do we know? No. And I want you to think about what I had said earlier. If I make a supersaturated solution, you remember what I said? What I do? I just dump some solid in there. So guess what I'm going to put for my initial amount of barium fluoride? I'm going to put the word solid. And I'll explain my reasoning. You can kind of try to marinate on it. Okay. I don't have to measure it out because it's going to be visual to me. Okay. So how much barium and fluoride would be in the water originally before the solid begins to dissolve? Nothing. Now, if it wasn't pure water, it might be a solution with barium or fluoride. So like if you're on city water and you try to dissolve barium fluoride in city water, what does city water have in it? A little bit of fluoride. And so you would have an initial measurement of fluoride. It'd be really, really tiny, but this is going to be tiny anyway. Okay. Okay. So do I know how much dissolves? No, I just give it some time. So here we are. We are in a situation where I don't have a clue. If I did have a clue, I would use that. But if the solution is at equilibrium, the change factor is going to be X. So the amount of barium fluoride, if I don't have any measurements, if I know nothing, the amount of barium fluoride that dissolves is X. So I'm going to put minus X. And so X is the amount. It's going to be an unknown. If you know it, like here, if you know it, you put a number. If you don't know it, you put X, just in a regular rice chart. If you don't know, it'll be the change that you don't know. Okay, so X is going to be our unknown amount that dissolves. So X amount is going to create barium ions and fluoride ions. So how much barium ions will there be? Plus X. And how much fluoride? Plus 2X, because change is always a mole to mole ratio. So at equilibrium, which is this situation right here, barium fluoride, what will we see visually and not have to measure? We will see solid. Here's our example right here. Okay, you'll see solid. You don't need to know how much, because what we care about is X. Care about the X, not the solid. So how much barium is there? There is X amount of barium ions. How much fluoride? There is 2X. So put that in parentheses, 2X fluoride. So our measurement for barium is going to be X, and our measurement for fluoride is going to be 2X.